So, continuation of previous previous class we discussed how to calculate potential at point P due to a point charge. Okay, so here we discuss potential maximum actually here at the surface of the sphere, potential maximum here at that point, and if R is increased then potential is decreased. But inside the sphere the potential is constant because electric field is zero inside that sphere. That's called a point concentrated at a point charge as concentrated. If R is much radius is a much smaller than that R. Okay, small R. Now we calculate another important board exam potential due to an electric dipole. Potential due to an electric dipole. And you know that what is dipole actually. So dipole is a two charge. Okay. So the configuration is like that is a two charge. One is minus q, other is a plus q charge, separated some distance. Some distance, that is a dipole center. If that distance a and that distance also a. Okay, so calculate electric field, calculate potential at some point P here. Calculate Vp. So the dipole moment vector from minus to plus in that direction, it is a P dipole moment. So calculate electric field potential. Sorry, it said rapidly. Right. So that a potential actually, potential at a point P. So that is a distance from center of the dipole to point P is R. Okay, and that distance, suppose from positive Q to that P to, so that is R1. Let's say the R2. Okay, that's the dipole center. So here we see the diagram very carefully. So potential P, that is equal to potential of minus Q plus potential of plus Q. They obey actually superposition principle. Okay, the basic and previous like a electric field and electrostatic potential. So like electric field and electrostatic force. Okay, they are all obey the superposition principle. So okay, so potential at minus Q, you see that that is R1 is greater than R. Okay, so that's why I need some correction here actually. If I increase that R and draw from a perpendicular from, okay, that's 90 degrees, and that angle is a theta. This angle also with a theta because they are vertically opposite. Okay, two lines intersect each other, so that is a vertically opposite angle. Same from plus Q to draw a perpendicular to R. That's 90. Okay, so potential at minus Q charge, potential independent of test charge. Okay, independent of test charge, and potential is a scalar quantity. So a minus Q, that is equal to minus Q over 4 pi epsilon naught, and the distance, okay, from R1 from the origin, if the distance is A and R1 here, see that R1 is greater than R, so near needs some correction. So the R1 equal to that distance is needed. Okay, that angle is theta. Okay, 90 degree. That is the hypotenuse. That is the base. So hypotenuse by base, the relation is that trigonometric ratio is a cos theta. That is a cos theta. Okay. So that now that R1 minus R, that is equal to A cos theta. So R1 equal to R plus A cos theta. Now R1 replaced by the R terms. So R plus A cos theta, and potential of plus Q charge. Okay. So plus Q charge, that is equal to plus Q over 4 pi epsilon naught R. So here that is R2 for plus Q, and the R2, that angle is theta, so near R2 is less than of R, so need some correction here obviously. So that length is A, 90 degrees, so this is also a right angle triangle. So this side is a cos theta, so that says also that if the angle of theta is a perpendicular, opposite of 90 degrees is a hypotenuse, and rest of this is a base. So hypotenuse and base, the relationship of trigonometry ratio is the cos theta. Similar that A cos theta. So here the correction is R2, that is equal to R minus A cos theta. So now the R2 replaced by the R minus A cos theta. Now take a common Q by 4 pi epsilon naught in both, and if I put the first one over R minus A cos theta minus 1 by R plus A cos theta. Now there is some algebra, Q over 4 pi epsilon naught. So you know the potential is a scalar quantity, okay? Potential due to an electric dipole, that potential is a scalar quantity. And taking LCM, R minus A cos theta, R plus A cos theta. So here R plus A cos theta minus R plus A cos theta. So cancel out these two R. So that is equal to Q over 4 pi epsilon naught, that is twice A cos theta over R and R, that is R square, and A cos theta minus A, that is A minus B and A plus B, A square minus B square actually, A square cos square theta. Okay, now here some apply boundary condition. Applying condition is that if the R, this length R, from dipole center, that is a DC, dipole center to at point P, the R is much greater than A. So if R is much greater than A, so ignore that this term. So Q over 4 pi epsilon naught twice A cos theta over R square. Now see that very carefully, that is a 2A has a Q, that term is called a dipole moment. That is P equal to 2AQ. Is a vector, so that is a P cap direction. Unit vector, so unit vector magnitude is a 1. So we get a Q over 4 pi epsilon naught, sorry, not Q. Okay, so now replace this, that is a P, okay, vector, and into the cos theta over R square. Okay, now if I change these two, if P vector and introduce a dot product of R cap, okay, so P dot R cap, so R cap unit vector is a 1, so that's a cos theta. A dot B, AB cos theta, so P magnitude, consider there is a magnitude 1 of cos theta. So P dot R, that is 4 over epsilon naught R square. the potential at point P. So see that very carefully that potential at point P, finally get the result is Vp P vector r cap, the direction 4 pi epsilon naught over r square. So see the very carefully the dipole moment, and here is the 4 pi epsilon naught is a constant, a Coulomb constant, or electrostatic force constant is a constant, it is r square. So you see that the V is inversely proportional of 1 by r square in dipole. Okay, if the point P at infinite, okay, suppose if I say condition if P at infinite, so infinite that means potential is that is equal to 0 if P at infinite. Okay, means that more and no distance is less than the potential actually. Means more r means a distance less actually here, that is inversely proportional. So potential max, so potential max, that is some dipole axis. So if r is more, so potential is less, inversely proportional. So if r is less, so potential is more. So if r at dipole center, if the r, or say that P at dipole center, we get V max. So potential max at that point. So here we get a maximum potential, get V max at dipole center. Dipole center we get a maximum potential. So V max, that is equal to the P vector, suppose that is a vector, magnitude is 1, unit vector magnitude 1, that is 4 pi epsilon naught, that is r square. That is the dipole center actually. Maximum potential we get a dipole center. There is some note, important key note here, write down the key note. The note number 1, potential due to a dipole, potential to a dipole depends not just on r, not just r, the distance r, but also depend angle between the position vector, but also depend uh, the angle between the position vector. The angle between the position vector. Position vector. The position vector. Okay, and the dipole moment P and dipole moment P is P also a vector. Okay, and axial symmetry. Here you get axial symmetry. You see that very carefully. That is actually axial symmetry. If I same thing this, if I axial symmetry is the same direction. If I take front to place a mirror, so take a mirror image. These are called axial symmetry. Look like this. So in case of axial symmetry and axial symmetry about P. P. If rotate the position vector, if the position vector, if rotate the position vector r about P, r about P, and theta is fixed. fixed, the point corresponding to the P, the point to the P generating same potential. Okay. So means say that if I take a mirror image of these and take a mirror, frontal-place mirror and mirror image and calculate a potential same that point P, we get a actual same potential value because the potential is scalar quantity, it doesn't depend on direction either plus or minus sign. Okay. And another important point is that number 2 point, potential actually depending here the V max depending on 1 over R square, not as 1 over R, because for point charge that is potential depend on 1 over R, but here the dipole the potential depend on 1 over R square. That's very important. Okay, for dipole that's single charge, that's the very important to key point. Okay, next we discuss calculate potential due to a system of charge. Calculate potential potential due to a system of charge. So consider there is a multiple charge here. Okay, very easy concept. There is a multiple charge. Suppose that Q1, suppose another charge is Q2, suppose another charge is Q3. Here that some distance we get a Qn. Calculate potential at here. Okay, potential at point P. Total potential at point P. So that distance is R1P. If the distance is R2P, the distance is R3P, and that the distance is RNP, Qn of charge. So potential Vp, actually they obey the superposition principle, means they follow the superposition. Okay, so potential Vp due to a Q1 charge 1P, we get a KQ1 by R1P, V2P from these potential at P due to Q2 charge, K Q2 of R2P, potential at 3P, K Q3 R3P. So potential at NP we get K Qn, okay, RNP. So total potential, the superposition pieces just algebraically added. Okay, so that total potential Vp we get some algebraically added. So V1 plus V2 plus V3 dot Vn, and we get V1 equal to K, some constant, Q1 by R1P, K Q2 by R2P, K Q3 by R3P, dot K Qn by Rnp. So K, take a summation, I equal to 1 to some case n number, okay, Qi by Rip, that the potential at point P. Okay, clear? Potential. If I consider the continuous charge distribution, if we choose continuous charge distribution. So means we get characterized by the density of charge density. Okay. So that is a charge density, charge density, that is equal to charge over there is some volume delta V, or delta Q by delta V, or Q over V. That is Q equal to rho times V. Now if I calculate the total potential Vp, here is some K outside the integration. The charge Q here replaced by the rho V, here rho dV, the volume integral over R. Okay, there's a volume integral R. So finally get the potential point P, 1 over 4 pi epsilon naught. So rho dV over R. That's a, if I continuous charge distribution. Okay, if you choose a charge distribution is a continuous. So if I not added single, okay, by one is a too much take a time, but the easiest way to can solve by the integration. Okay, the help of calculus. And Q rho B, the charge can determine the potential of each element. Okay, and here the important point, Q rho Q equal to V, or consider the small amount of V, small amount of V, charge carrying determine the potential of each element. Determine the potential of each element. Okay, and here we see that in previous we discussed some the charge configuration actually. Here the concept, suppose in previous, in see that diagram actually carefully and read out the diagram here. Okay, clear the previous concept actually. What is the rho charge rho dv? That's the integration. Okay, because there is a summation actually. You can, if I skip the summation, we can add it too much. Single by single add is taken too much time. That's why you solve the help of integration, the calculus method. That's very easy. Okay, now see that in that case. Okay, so potential at a point P here. So potential at a point P, okay, that is equal to 1 over 4 pi epsilon naught. That is a charge Q over R, and this R is much greater than capital R. Okay, that is outside the sphere. That is outside of the sphere or the charge of sphere. Okay, outside that point charge or sphere of charge contained. And if inside a sphere, that is equal to 1 over 4 pi epsilon naught, that is Q over capital R. That is the maximum potential. Okay, at the surface or inside the surface. The potential at the surface is this, and that is the maximum potential. We know the diagram is, if a potential versus calculate the R, we get some point here. Okay, that's the maximum point. At this point is like a potential. Okay, so 1 over 4 pi epsilon naught Q over capital R. Okay, so at the surface, at that potential, same as that potential, same as that potential, even same as that potential also. If I calculate potential at center of the sphere, same potential value at that point. So uniformly charged spherical cell. So mm, charge spherical shell. The electric field, the electric field outside the cell, right? Cell, cell, as if the entire charge, as if the entire charge, the charge is concentrated at the center. Concentrated at the center. The center. Okay, clear? Calculate potential at point charge or potential at dipole concept. Okay, if I calculate a potential of multiple charge also, we solved it. Okay, that's the multiple charges. Okay, a system of charges. Okay, so next class we discuss equipotential surface, calculating potential from a field, or what is equipotential surface, a concept of equipotential surface. Okay, so today end the class here. Thank you.